of copies of the initial expression. And then we will use our round of error analysis to compute a worst case absolute error that will denote the fitness. So the smaller the error, the fitter the expression. So the better the expression is. Initially, all of the expressions will have exactly the same error because they're just copies. Then we will iteratively pick one of the expressions from our population and mutate it using some real valued identity. That may or may not reduce the round of error. So in this case, this rewrite has actually reduced the rounding error by nearly 50%. And we will repeat this for the other expressions as well. So we will get then different rewritings with the different fitness values. And we will repeat this loop. But the point is that whenever we pick an expression that will be mutated next, the probability of picking the next expression is guided by the fitness. So this means that expressions that already have a smaller error are more likely to be picked and mutated further. But also expressions that have a larger error are still possible to be picked. Now, this second point is actually important so that we do not get stuck in a local optimum. Now, when I learned about genetic algorithms in my undergrad studies, I never thought I would ever use this because this sounded like really crazy, but it's actually quite effective. So once we have an actual order that is good, we can then start assigning a finite precision to it. And let's go back to the rigid body that we had before, and let's just pretend for now that we have only the arithmetic expression. And let's suppose that the user has said that they need the implementation with an error of at most 1.75 to the 10 to the minus 13. Now, our tool can only compute an error of 3.5 for a uniform double precision. So that's not going to be enough. So this means that we will have to pick the next higher precision to satisfy this error bound. The next higher precision would be something like quad that is implemented in a library. That will satisfy the error bound by a huge margin, but it is also going to be significantly slower because now it's going to be implemented in software. However, if we use mixed precision, so we assign different operations to different precisions to different operations, we can still satisfy the error bound and be around 28% faster than the uniform quad precision. So here, for example, we can do 3 operations still in the lower double precision, and we only have to upgrade 4 of them. Now, again, we would like to do this assigning of the different precisions fully automatically. And again, the biggest challenge is that we have a huge search space and we cannot just go through all of the possible combinations. So we're again going to do an incomplete search. And I'll quickly try to explain how we do this. It's a little bit like a divide and conquer. So we start off with all of the arithmetic operations assigned to some high precision. And we will first double check that at least with the high precision, we can satisfy the error bound. If this is the case, we'll try to assign the next lower precision, in this case, say double, which does not satisfy the error. So we need to find something in the middle. For this, we will split the operations and we will assign half of the operations a higher precision and half of them a lower precision. And we will check again with our round of error function whether this satisfies the error bound. If it does not, then we will continue splitting until eventually we will find some assignment, some mixed precision assignment that satisfies the error bound. And then we will use a static cost function to pick the one from the available assignments that should have the smallest running time. Now I talked about 2 different optimizations. One with the rewriting that improves the errors, so increases the accuracy, and the mixed precision assignment that improves the performance. So it suggests very much that we should combine these. And it turns out that if we combine rewriting and mixed precision tuning, we can improve performance even more. So the idea is that by rewriting, we improve the error and give the mixed precision tuning a little bit more to work with. So we can reduce some more operations to the lower precision. And in fact, for our example here, instead of 3 operations in doubles, we can now have 4 of them. And this means that the implementation of this is going to run about 43% faster than a uniform quad precision that we would have to use in the absence of mixed precision. So that's optimizing the arithmetic. Now let's look at when we have elementary functions, such as sine and cosine. Now, these do appear quite often in numerical code, in embedded systems or scientific computing. And usually what people will do is use a library function, which is convenient, but it provides only a very limited choice of precisions. So if we're stuck to just floating point arithmetic, then we only have single and double precision. However, especially when we want to look at embedded systems that would be implemented on FPGAs, we would want to use fixed point implementations that provide a much wider range of precisions. So in practice, you can use any number of bits for any operation that you want. So some operations could be implemented in 7 bits, others in 32, depending on what you need. And you could use, for example, our mixed precision tuning to determine which bit length you want to have. But for the elementary functions, you would still be stuck to just 32 or 64 bits. So our goal is to synthesize polynomial approximations of these elementary functions that are specialized for a particular input domain. So in this case, are specialized for having inputs like x and y that are only between -2 and 2. So we do not have to have a completely general implementation. It only has to work for this particular function. And it should have a guaranteed end-to-end error bound. So this means that this end-to-end error bound accounts for both the approximation error of the transcendental or elementary functions, as well as of the arithmetic errors due to the fixed point implementation. So, and we want to have a fixed point implementation because it gives us a much wider range of precisions that we can use. Now, the challenge here is really, we have an error budget at the end of the program, and we need to distribute this somehow so that we know how much of this error budget we can use for the arithmetic and how much do we have to assign or use for the approximations of the elementary functions. We distribute this error budget in 2 steps. We first do a global distribution, so a very high level distribution where we distribute it to the elementary functions. And then within the elementary functions, we do a local error distribution that again distributes between the polynomial approximation and the arithmetic implementation of that polynomial approximation. So for the distribution of the global error budget, this distributes the error budget that the user specified at the end of the function to the top level arithmetic and the individual elementary operations. And for this, the key idea for how we do this, we use the mixed precision tuning that I explained before. And we just pretend that these elementary function calls are just like arithmetic, just with a slightly larger error, because that is what we will have in practice. Now, the errors cannot be very different because otherwise one would dominate the other and we could then find a better distribution. So we will just abstract the approximation errors from these elementary functions and just pretend that these are just round-offs. We do have to account for the higher cost, but this we can do with an abstract cost function. So then once we know for each individual elementary function how much error we can use, we still need to decide how much of that to actually use for the polynomial approximation and how much to use for the actual implementation of that polynomial that we then get. And we'll do this, we do this with an iterative feedback loop because we could not find some a priori way of splitting this. So we will first try to increase and decrease the elementary function budget and use a cost function to estimate the performance. For the polynomial approximation, we use some numerical analysis theory. So there are tools and theorems that give you the best polynomial approximation. So this means that for a given degree, it will give you the best polynomial that has the smallest error. And we can also do domain splitting, so we can have for certain subdomains a different polynomial than for the others to get an optimal error. However, this theory can only generate the polynomials, and the tool in particular only can only do floating point arithmetic. So we still have to do the fixed point implementation ourselves. So what does this tool return? For example, for the sign call, for our example that I've showed you before, it would generate something like this. So it will generate a piecewise approximation of the sign function as two polynomials. But these are still in real arithmetic. So now we need to use our precision assignment to actually implement this in finite precision. So, and finally, just a small hint, what do we get out of this? So we have tried a couple of benchmarks that would be roughly representative of what you get in a small embedded system. And we compared the performance of our generated code on an FPGA against the implementation that you would get with the standard library functions. And on average, our code runs around 45% of the time that the library implementation use. So we're not uniformly better. For some benchmarks, the libraries are still more efficient, but for most of the others, we run about 2x faster. All right, so that's the state of DAISY right now when it comes to approximations. So I would say that at least for these small arithmetic expressions, we have more or less achieved the stream of this approximating compiler. What we want to do next is scale this up to bigger programs. And yeah, we'll see where that leaves us. Any questions? And now, do I stop screen sharing, or because otherwise, do I see people? No. So I'll just leave this open.
Okay. Okay, thank you, Eva. Wow, there's a lot going on to get this to work. A lot of algorithms and tech. I was wondering, so one thing is everything is static, right? And would there be any advantages to try to do things dynamically, like bound the errors dynamically?
So we do have some dynamic analysis in DAISY as well, because in certain cases we also thought, well, the over approximation in a static analysis can sometimes be big. So in certain cases it may be advantages. In others, it's not. And one of the things we have, for instance, observed, if you want to get an accurate estimate of the error with a dynamic analysis, you have to run a lot of inputs. So it's actually going to be slow. So the static analysis is actually much, much faster. Mm-hmm. Now the errors, the static errors that we compute for the arithmetic of the expressions that I've shown you, they're usually accurate to about an order of magnitude. So that's actually not that bad.
Okay. Let's see if there's questions in the chat.
Can I just jump in with a question if there's none?
Yeah, go ahead.
Okay, excellent talk. Very enjoyed it. I was thinking, when thinking about the scientific computing part that you mentioned, there's a lot of iterative solvers where, like floating point errors can propagate through the iterations. Is that something that you have in mind to also address, or at least think about it?
Yes and no. So if you have an iterative solver, then I would argue that most of the time the errors do not really propagate in the same sense that I have talked about here. For most of these iterative solvers, you can think of every iteration just restarting from a new starting point. So the error that you accumulated before doesn't really matter so much, or at least it doesn't make sense to really propagate them through the iterations. What would make sense, though, is if you look at only the loop body and try to optimize the loop body itself. And I think that can potentially help to maybe speed up how how do you say that now? I forgot the word.
The convergence.
Convergence. There you go. Yeah, the convergence.
Okay. All right. Thanks.
Any other questions? Please feel free to jump in.
So maybe in the meantime, I wanted to jump in about the application domain. So you mentioned embedded systems, and how is Scala coping with that? So is it, I mean, are you thinking about, for example, compiling down Scala to native code, or is it sufficient? Or
so our input language is a DSL in Scala, and Daisy itself is implemented in Scala. And for that, I think Scala is very great. Is an amazing fit. That said, when we generate code, we mostly generate code in C, because ultimately this is what you will then run on an embedded system, or if you're compiling down to an FPGA, the high-level synthesis tools for an FPGA, they take C as an input. But for implementing an actual static analyzer, Scala, I think, is a great fit.
how do you do the compilation to C? Is it Scala native, or is it something you implemented yourself, or?
So it's very stupid. It's a simple pretty printer. So we have an internal representation as an AST, and we literally just pretty print it.
May I add or ask another question?
Yeah, sure.
When you talk about the reordering of expressions, what is the sort of the scope that you consider? Do you think like also like fusing statements to enlarge the actual analysis space for the expression rewriting, or do you consider one statement after the other?
So right now our rewrites are really just real valued identities. But as long as we can evaluate the error, it doesn't really matter what the rewrite looks like. So you could even imagine doing a rewrite that actually applies a polynomial approximation, as long as you can quantify the error by it. One rewrite that I'm not actually sure we have implemented, but that you could imagine is something like a fused multiply add that in general reduces the round of error as well. So the bottleneck is really we have to be able to analyze the error. The rest is easy.
Okay, so thank you very much, Eva.
Maybe if I may, the very last one. So you've been very quick on future work. So you said you want to apply it to larger programs, and that makes a lot of sense. But any more hint?
So there's really two avenues I would like to pursue. One is to make this whole analysis business more modular. Right now, we assume you have one piece of code, and that's unlikely to scale up. So we need to have a modular analysis. And the second one goes more in the direction of what Nada was alluding to with the dynamic analysis. I think that for many programs, you do not necessarily have to statically analyze the entire program, but you need to analyze the kernels that actually do the heavy numerical computation. In order to do that, you need to somehow get these specifications that the static analysis needs. So we're hoping that we can use dynamic analysis to get a decent estimate of what the specification is, so that we can then use the static analysis only on the parts where it really matters.
Okay, anything else? Okay, so thank you again, Eva.
And I'll stop sharing, I guess.
Yeah. So I guess Alex is up next. And Alex will talk about typeful functional deep learning .t meets an open AI standard. And that is an open source talk.
Hi, everyone. I'll just switch over to my slides now. There we go. I'll full screen it. Okay, so some background here. Of course, this is an open source project, so you can find it on GitHub, and you can find more about me on my LinkedIn, which is linked from my GitHub. I am an independent machine learning engineer, practitioner, mainly do contract work, but I've worked in a lot of different contexts and situations. And the thing is that I like Scala. I like the fact that it offers, type safety and the foundational element of functional programming in it. But in machine learning, deep learning, Python rules the roost. So most of the effort and most of the, the largest ecosystem is on the Python side of things. And so while I've been able to accomplish a fair bit over the years, primarily working in Scala and on the JVM, but there's always this drive pushing you back towards Python. And that's really the main motivation impetus for this whole thing. And then along the way, Dotty was emerging at the same time. So I thought, why not take advantage of some of the features there and, push this even farther forward. So just a little bit of background here on machine learning and deep learning and how it intersects with functional programming. There's a great paper here that I credited at the bottom there, but it says that in supervised machine learning, meaning in the context where we have a clear target and we have labels for that target so we can get an error on the output of our machine learning models. Model inference, that is prediction or running the model forward, not the training phase, but just the inference phase, is a pure parameterized function with a parameter space, and it's the function that we see below. A is the input, B is the output, and P are the parameters. They interact with each other, and that can be anything from as simple as matrix multiplication, and both A and P are matrices, or P can actually be a lot of different internal parameters and internal structure, represent a lot of internal structure and typically state, but we're looking at this from a stateless functional perspective. So there actually are two other functions that this paper refers to. Interesting, just take a look there if you have time, which explain how to create a fully functional, compositional, trainable machine learning system. The other two functions are required for the compositional training part, so I won't go into further detail here. But like I said, most approaches to deep learning typically are imperative, stateful. They mutate things. They use objects that have internal state that gets changed when they get trained. And they're dynamically duck typed. You get a lot of errors at runtime in Python. Sometimes after a day or even a week or whatever of running these very computationally intensive machine learning models. It'd be a lot nicer to get those errors at compile time. So at around the same time I was starting to look at this project, I mean, in the past I've used different interchange formats like PNML. They were kind of limited. There's this new open standard, new a few years ago, spec called Open Neural Network Exchange. And the goal is interoperability between, like I said, the mostly Python-based tools, but the fact is that the core spec is agnostic, and so why not build upon it to enrich the machine learning ecosystem in Scala. So in the meantime, this project was started by Microsoft and Facebook, but a bunch of other corporate backers and community backers have come on board, and now it's been brought into the Linux Foundation. And it supports everything from toy neural networks, which you'll see in the next slide, to state-of-the-art machine learning models like the multilingual text-to-text transformer. That's a paper by Google. It's published about a month ago. And it's possible as of yesterday, I think, to export it to ONNX format. So here's one of those toy neural networks that I was just talking about. In terms of the function that we saw earlier, A is actual input here. This is flowing from the top to the bottom. So you have the input, and then the what's called data here in the transpose box are the weights, the parameters, and then some multiplications happen. There's a nonlinearity. There's a second layer of more weights coming into this, and then a final nonlinearity, and then an output node. So this is about as small as it gets for a neural network that can really generalize. And depending on how large how many nodes you have internally there, it can actually represent one quite a bit. But So we're going to use this going throughout the rest of the talk to compare how this looks in Onyx Scala, and eventually something that's actually even a little bit nicer that's built on top of Onyx Scala. So continuing on about Onyx, it's an intermediate representation. This is all laid out on their website. It's a format for representing both the structure of the model, neural network models, and the data that is used as input and output. It defines data types for inputs and outputs. The spec supports all of the standard Java, Scala, primitive numerical types, but it also supports a number of other like unsigned int, say, complex numbers, a couple of different float 16 variations. It uses protobuf to encode tensors, often alternately referred to as n-dimensional arrays, close enough. And it encodes models, which basically are some metadata and a graph. And then each graph is composed of a number of nodes that are connected. The outputs of one node feed into the inputs of another node. And it encodes weights, which are those things that are typically mutable in the less functional approaches to these things. But in Onyx, they're immutable, really. And attributes, which are the things that are normally immutable that are not updated iteratively over the training process. This is defined in protobuf and in operator schemas defined in C++, although actually there are some things that I came across recently that are not really documented in any of those things. They're just documented in text. And I've been incorporating some of those things. So crucial point here is a graph from the Onyx docs. A graph is used to describe a side effect-free computation, a function. Because Onyx didn't support training from the get-go, it was really, really focused on inference. That means that it is functional already. So that's a great basis for us to build on. Design goals for Onyx Scala. Like I said, I want to take advantage of what Scala can offer and ultimately what Dotty can offer. And some of these types that I'm referring to here are only possible to support in Dotty. But it's typeful in the sense that it encodes at the type level the data types, the float, whether you're using float, double, int, etc., which you might be surprised is not even, you can fail on runtime on incorrect data types being fed into things in Python. Happens all the time. The rest of these are less commonly touched on, and there are a few, you can find citations at the end of this for projects that have done some of this, but not really fused it all together in the way that I've done here. And there's some motivation for this in the Onyx spec for tensor and axis semantics. And you'll see what that is when I get to it in a few slides. And for shape safety, to make sure that you aren't passing incorrectly shaped data, incorrectly shaped tensors into nodes or into entire Onyx models. And looking for functional machine learning inference in Scala, like I said. So in the end, I ended up using, there were other solutions for this earlier on in the process, but now there's a really nice sort of canonical backend for Onyx called Onyx Runtime. And it supports CPU and GPU, and now it has a Java API, which I'm able to use. And there's also a JS backend that I kind of have baking now. The interaction with Dotty is a little bit problematic, so it's not fully fleshed out yet, but that's coming soon. And the idea was then, in addition to just being able to use state-of-the-art machine learning models, call them and get outputs, I also wanted to create a domain-specific language for Onyx. And originally I wanted to generate programs from the Onyx files into programs in Scala in terms of this DSL, and I did that, but I found that that's actually not the most useful use case for this. So Onyx Scala has two APIs. The first one you'll see here is a full model API. It's a black box form of execution. It's very simple. It just loads at runtime an Onyx file and passes it to the underlying backend. That allows the backend to do full graph optimization, some really nice performance optimizations. This API has minimal type safety, and the performance is pretty good. There is some overhead. I'll talk about that a little bit later, but for off-the-shelf models or performance critical scenarios, this is the preferred API. Here's an example of it. The first block is just setup. We load the Onyx bytes from the file. We instantiate a backend there with it. And then you start to see some of the typeful stuff that I was talking about. First, there's just the raw data. Here, this is an image classification problem that we're looking at, but I just filled it with 42s for the purposes of this. But below that, you have the shape. 1, 3, 224, 224, and you can actually see the denotations, the meanings of those axes below. 1 is batch, 3 is channel, RGB, and then we have height and width. And we also have a denotation for the entire tensor, which is to say that this thing is an image. Then you create the tensor with the data and the denotations and the shape, or if you don't really care about the denotations, which in some cases you might practically not, it's more succinct. You just write it without, just with the data and the shape. Then this is where we actually get to the good stuff. We run the full model in the next block, and finally we get an output with a shape, and which we can. This is, like I said, this is an image classification problem. There are 1,000 different classes. We just take the max predicted probability, and we get 418, and that says that this is a ballpoint pen. The second API that we have in Python-Scala is for everything else, basically, when you don't just have a single large computationally intensive model that you just want to take off the shelf. And there are models for these things. You can find many of them. It's actually very good, this state of sharing these models these days. But there are lots of other things that you need to do, like pre and post processing, like so just maybe transforming the outputs, like doing the training somewhere else and having a streaming setup, and those internal parameters that are normally mutable, you could feed them in here and live through parameter streaming. You can do transfer learning by taking those pre-existing models and then doing some interesting things on top of them, manipulating their outputs, doing an extra layer of learning on top of them, and you can ensemble things by combining together different models. All of those tasks are what this fine-grained API is mainly intended for. It has a minimal tensor type, and this API is really where the type safety comes into full flourishing. The tensor type itself is shared between both APIs, but the operations, which we're going to get to right here on the fine-grained API, is where it's different. So the ONNX operations are realized here as version numbered methods on traits. So we're never going to have changes in the background. Once a version is published, it's final, and these are stateless functions. And this was originally I had a generation step generated from, like I said, the protobuf and the C++. Now it's manually curated because, like I said, there are certain things that can't be generated, and also there's a whole new metaprogramming environment in Dotty, and I haven't had a chance to move to using that for the generation step yet. And the ONNX graph now is just a program in terms of this DSL. And then how about performance on this one? The performance depends on the number and size of operations. So if you have a lot of operations operating on small data, then there's going to be a lot of overhead. I was actually surprised, though, that comparing this against NumPy, which is the standard library for numerical computing in Python, originator of the ND array abstraction, or at least popularizer in recent years. And NumPy, I wasn't that surprised to see that when it's using open source linear algebra libraries, we can beat it using ONNX runtime. But actually, at least in some limited scenarios, possibly more, I haven't done really extensive benchmarking, it can actually be faster than NumPy with MKL, which is a proprietary optimized Intel library for linear algebra. And ONNX runtime itself doesn't use anything proprietary. It has an open source linear algebra library created by Microsoft under the hood. But it can also, this API can also be a lot slower. Like I said, if there's a lot of small operations, that's because of different sources of overhead. We have JNI, which, because this is a native library that we're interacting with, so there's by necessity, there is copying overhead. But surprisingly, despite all of this being functional and there being copying and everything else, like I said, it actually is surprisingly performant. There's also additional overhead for creating the ONNX model and graph around the operations and converting them into bytes, and then processing and unwrapping that on the other side. And there are improvements on the horizon in ONNX going to expose these operations as actual usable functions in ONNX runtime, I mean, which could remove that source of overhead anyway and give us a nice performance boost. But so here's the fine-grained API, how to use it. Similarly, you set up a tensor, maybe with denotations, maybe not. Like in the previous case, now you have fine-grained backend. You call the absolute value function version 6 from the ONNX spec of this. You call it on a long tens with a negative content, and as you would expect, you get positive. Here's some of the type safety in evidence. You can't take a square root in ONNX of a long. It's an int in type. So that's forbidden, and we get a compile time error saying constraint not met, because the constraint says it goes off the side of it. It says that it's float types that it wants. And then here is that simple feed-forward neural network that I was talking about before in Onyx-Scala. It's relatively readable, relatively straightforward translation, but it's still not super nice and concise and fluent, and it doesn't look like the Python equivalent. So here's another project that I've created recently that's an interop layer between what we do have available in the JVM and in Scala for machine learning and Onyx-Scala. And it's a lot smaller, a lot cleaner, a lot more readable. And this is the forward pass. And then just as a bonus, here's what a backward pass would look like, which is what is required to actually do training and do the learning part of deep learning here. Just about done here. So the typeful and functional highlights. Like I mentioned, it's polymorphic in the data type. They're using dotted union types there for type constraints. It has typed, tensor, and axis semantics and shapes, and we have supporting dotty features for those like compile time singleton ops and match types. And the shape and axes types are appropriately transformed on the operations, like I mentioned earlier. So if we transpose a matrix or a tensor, or reshape it or do reductions on it, which change the number of axes, then that's handled correctly. And this is all stateless and referentially transparent. And that's it. That's all there is to it. Future work, like I said, training is something that's missing from this by design in Onyx, but in more recent versions, Onyx has introduced limited tech preview support for training, and so is Onyx Runtime. And also there's the possibility of implementing our own automatic differentiation scheme on top of this. And ultimately, it'd be really nice to see fully differentiable functional programming in Scala, Dotty. That's about it. Any questions?
You can also put your questions in the Clouder chat. So I guess I'll ask a question. Have you used this in Anger, like for actual client projects?
Yeah, so far I've deployed one project to production using this, which was a deep recommender system. And currently I'm building on top of that text-to-text transformer work that I was talking about, implementing a multilingual sentiment classification system
Cool.
using Onyx-Scala. I did it first in Python, and now I'm porting it over to Onyx-Scala.
Okay. Well, so maybe to catch up on time, maybe we should move on if there aren't more questions. So I'm not sure, David, can you say who the next speaker is?
The next speaker would normally be Mohammed Ashuri, but I think he's currently not here right now. So in that case, we would ask Ifas maybe if he can give his talk right now.
Yeah, I can do that, mate.
Thank you.
No problem.
So Ifas is going to talk about a simpler syntactic soundness for dot. So yeah, so there has been a range of simplification of soundness groups. So I'm curious to see what this one is about.
Okay. Let me share my screen. Can we? Okay, this is on Zoom. Screen. All right, can you guys hear me?
Yes.
Okay, in that case, I'll start. All right, hello and welcome. So I'm going to be talking about a small simplification to the syntactic soundness for dot. There's been, as Nana said, a range of simplifications. So this is, in some sense, the latest thing that we've simplified. So let's get started. Slides are being difficult. Okay, so again, I'm talking about dot, which stands for dependent object types. And the dependent object types calculus is a foundational calculus for Scala. It features path-dependent types, and that's its main focus of formalization. And Dot is somewhat infamous for having a very tricky type safety proof. Let's talk about path-dependent types a little. So in Scala, objects can not only contain like fields that have references and data, but we also have fields that contain types. These are called type members. And types can refer to these, you can have types that are these type field selections. So you can have this path-dependent type, this.fruit.a, which is path-dependent on this.fruit, the path. So in this talk, I'm going to be talking about how hacking value typing can be used to simplify the Dot type safety infrastructure. So what is type safety? Right info license says that type safety is just proving the progress and preservation lemmas. I'm mostly going to talking about the progress lemma, although similar ideas apply to the preservation lemma. So what is progress? Progress says that if you have a well-typed machine configuration, then you've either you're either done with all your computation and you've reached an answer, or the machine can take further steps. And the main thing is that the machine is never stuck. So how do you prove progress? You prove progress by an induction on the typing relation. So the typing relation will have cases for values and basic operations such as function calls and field reads, some compositional cases in Dot, that's just lead bindings, and it'll also have a subtyping case. In Dot, all of these cases are easy. Values are already answers. For the compositional cases, for example, lead binding, if you have let x equals t in u, you can step to executing t. So that's how you have taken a step for progress. And the subtyping case is also easy because if you have t has type t, and by supertyping has type u, then the induction hypothesis says that t has type t and t steps or is an answer. So you just use the induction hypothesis for proving progress. But when you get to the basic operations such as function calls or field reads, it gets difficult because the main source of this difficulty is that you have to invert a reference to get to a value. So if you have a reference x, you have, and you're trying to do a field read x.b, then you have to somehow show that x refers to some object with the field b, and subtyping in Dot makes this very difficult. So what about subtyping makes this difficult is in Dot, we have this wild subtyping rule, which says that if x has, if x has a type member A with a lower bound of t and upper bound of u, then t has to be a subtype of u no matter what t and u looks like. So if you think about what if t is an object type and u is a function type, right? So this it's very odd for an object to be a subtype of a function. So let's look at an example. So if you have this typing context where x has this object type with a type member A with a lower bound of, again, another object type, an upper bound of this function type, then by the subtyping rule we saw earlier, you have that the object type is a subtype of the function type. And now, since x has this object type, x must also have this function type. This is very odd. X has suddenly changed shapes from being an object to a function. And you can use these typing judgments to show that some weird functions exist in Dot. So here we have this function that appears to coerce x from being an object to a function. And this is a completely well-typed term in Dot. Again, it's closed, so it doesn't even need access to some external typing context. It is just in an empty typing context, we can type this lambda. But despite all of these craziness, Dot is still type safe because in Dot we can never create objects which have type members with these wild upper and lower bounds, because we have to always assign a real type to an object's type members, and generally you don't have types with which have an upper bound of a function type and a lower bound of a object type. So although the function we saw earlier is well typed, it can never be called at runtime. But path-dependent subtyping has its uses. I'm not going to get into this talk, but the wild subtyping rule, although it's crazy, it does have its uses. So let's talk about the dot type safety infrastructure. So I'm going to be talking about our OOSLA 2017 type safety infrastructure, which relies on inert types and inert context. And one of the main things that we use is for inert types, we use less wild typing relations. And then we show that it produces the same types when you're in inert context. So what are inert types? Inert types are just object types where the bounds are tight. So if you have a type member A, then it has to have the upper and lower bounds match, or it can also have a dependent function type. And inert contexts are just typing contexts which map variables to inert types. And our proof infrastructure starts off with general typing, and we show that if you have inert context, then general typing is the same as tight typing, which in turn is the same as precise and invertible typing for values and paths. I'll get into what tight, precise, and invertible typing are in a bit. So what is tight typing? Tight typing says that values, in tight typing, values are typed using just general typing and subtyping. And otherwise, we use different subtyping rule when you're trying to figure out subtyping between paths and other types. So this is a less wild subtyping rule where we say that if you have tight bounds, so the upper and lower bounds match on the type of X, then X.A is a subtype and supertype of T. This is the only change we make to the overall typing. Otherwise, it's very similar to general typing. Precise typing for values uses only value introduction rules. There are no subtyping involved, and it's directly invertible. So if you have that, a value V has some recursive object type, then that value has to be an object. Precise typing for paths only uses elimination rules. So if you have that X has type, X has the intersection type of T and U, then individually X has type T and X has type U. Invertible typing is just typing without any sort of shape shifting. So you'll have rules such as this. If gamma says that S is a subtype of T and X has some object type with these bounds T and U, then X also has the type of type member A having a lower bound of S and upper bound of U. And we, in our OOSLA 2017 paper, we provided a proof recipe, and the proof recipe works something such as the following. So suppose you have X is an object, or X has this object type, and gamma is an inert context. Then X has the type, same type because you're in an inert context. Similarly, X has this invertible type, again, because you're in an inert context. And by again, because we're in an inert context, we know that X also has this precise type, where some of the type might be a little more precise. So you'll see that we changed from B having a type U to B having a more precise type T, where T is a subtype of U. And by inverting precise typing, we know that X has to have this recursive object type, where B is a field inside this object. So that's one half of the proof recipe. So we have, we went from the type of X to the type that's bound to X in the context. We now have to go to the value that X refers to. So suppose you have a heap or store sigma, and gamma types all the objects in the heap, and gamma is inert. Then by inverting the heap or store correspondence relation, we can say that the value referred to by X in the heap has to have the recursive object type. Similar to above, it has to have the same precise and invertible type. And again, the same precise type. And then from the precise type, we can invert this to get to the actual value in the heap. So we went from saying that, oh, the value has this object type to the value is this object with a field B. So in this work, and this talk at least, will show that if we do some hacks, then this entire second page of the proof recipe becomes unnecessary. So this entire second step goes away. And we also simplify the infrastructure we need. So the simplification will happen in 3 steps. We'll first simplify type typing. In the second step, we'll use a much stronger heap or store correspondence relation. And in the third step, we'll remove precise and invertible typing for values altogether. So let's simplify type typing. If you looked at our proof recipe diagram, you'll notice that our recipe only uses inversion. We only need to go from path to a value. So we don't really need type typing for let bindings or function calls or field reads. So we remove type typing for those cases, and then we end up with a proof infrastructure that looks like this. So we split up type typing into type typing for values and type typing for paths. Type typing for values and paths. In step 2, we use a much stronger store correspondence relation. So we use precise typing for store correspondence instead of general typing for store correspondence. This is very similar to what was done in the original Waterford safety proof. And the nice thing about precise typing is that it's directly invertible without using any sort of recipe. So now our proof infrastructure looks like this. We only have precise typing for values. We don't need special typing for type or invertible typing for values. In the third step, we use special value typing altogether. So precise typing for values is type the value using an introduction rule and do not apply any subtyping rules. That's what precise typing for values is. In Dot, values are typed as terms. So values are terms and there's no separate value typing. So what we do is we introduce a value typing. So we create a syntactic category for values, and we have value typing separately, and we do not apply any subtyping for values. And then we lift this to term typing. So if you have that a value has type T, you can lift that to the value as a term has the same type T. And then you can apply subtyping to this term, the value as a term. And now we have invertible value typing that's directly built into Dot, and we can use this for store correspondence. And this simplifies our proof infrastructure to just have general typing, type typing for paths, and precise and invertible typing for paths. We do not need any extra infrastructure for values anymore. So now our second page of the proof recipe looks like this, where you have if sigma is a heap and the typing context gamma corresponds to the heap, and the typing context maps the reference X to some recursive object type, then by direct inversion, you get that the heap, the object in the heap, the item in the heap has to be this object. Previously, we had a lot more steps that we needed. One nice thing is previously we needed inert context for some of this inversion, and we do not anymore. If you look at our GitHub repo, we've applied all of these simplification steps to the Wadler-Fritz dot calculus. There's also, we applied step 1 to the k-dot calculus. K-dot was already defined using the step 3 style value typing, so we did not need step 2 and 3 simplifications. For the p-dot calculus, we applied the step 1 simplifications. That's everything from my end. Thank you all for listening.
Thank you, Ifaz. Are there any questions? Please just feel free to shout out or put it in the louder chat.
Maybe in the meantime, a quick one. What's your intuition about the simplification for this proof? So after, I think the first one was Nado's paper, and then there was a sequence of papers that simplified this proof. How can it become even easier than this? Where are we going?
So I think we can have some more simplifications. So right now, we still have. So if you look at the rules themselves versus what's implemented in Coq, like the recursion between typing and subtyping in dot is between paths and subtyping. So subtyping depends on types or paths, and types or paths depends on subtyping. But what we have in dot right now is like at least what's implemented in Coq is subtyping depends on typing for terms, and types for terms depends on subtyping. Like the only other simplification I can think of is maybe have more control over like what subtyping depends on and what's dependent on subtyping. That's the only simplification I can think of. Going from what we have right now, I can't really think of what else might happen.
Any other questions?
Hi, I have a question.
Yes.
Is it possible to quantify how much the proof is simplified?
I guess we can take a look at how many extra proof rules we took out, but that's not a very good measure in my opinion. In my mind, all of this is just conceptual simplification, just having to think about like all sorts of different typing rules for values was very difficult for me. So for me, it was more about removing special typing for values and not having to worry about this was like the main simplification here. But you can quantify it in terms of like the number of rules removed.
Okay, great.
Okay, so thank you, Ifaz.
Thank you.
And I guess this is the break now. It's probably going to be shortened because we want to start at 12:40. Sorry, like I guess for everyone's time zone in 13 minutes. That's when we want to start. David, I'm not sure if you had more organizational things to say.
Yeah, I think it would be good if the author of the essay that's going to present soon can now mention whether they're here or not, and then we figure out in what order the remaining talks will be done.
Hi.
Hi. Okay, I see another author. That's great. Okay, everyone who is not an author of a paper can go into a 20-minute into a break until the next supposed time slot for an event is going on.
So do we have an author for the Scala Pi paper? Shadaj.
Should we send some email reminders? Maybe I can do that.
Yeah, it's probably a good idea.
I guess I can test that I can share correctly at this point.
I guess so, but actually currently Nada is host, so she has to allow someone to screen share.
Okay, I'll make you a co-host.
Great, now you should be able to test your setup. Great, seems to work. I can see some.
Okay. Wait, can you see the presentation or did it go to the other tabs?
I can see the presentation and full screen.
Okay, good.
Okay, good luck, Nicolas.
Thank you.
Hello, everyone.
Hi.
Hey, Martin.
Hi, Nada. How are you?
I'm good, thanks. How are you?
I'm pretty good. We had a beautiful afternoon, sunny and warm. So we just enjoy the last days before winter, basically.
Okay, yeah.
Are you in Boston or are you?
I'm in Boston. Yeah.
Okay.
It's pretty nice right now out, but yeah, it's yeah. I mean, the times are strange. I think I'm probably not gonna go home for the holidays because it's too complicated with the visa and the green card.
Yeah. We probably stay put as well. Yeah. You probably have read that we are sort of Corona hotspot of the world right now here in Swiss Romand.
Yeah.
So it's completely crazy, but nobody takes it very seriously. I have the impression. So yeah, but anyway, it's pretty much locked down. Yeah. I missed I only came at the tail end of Eva's keynote. How was that?
It was good. It was it covered a lot of ground, so a lot of algorithms and yeah.
Okay. Cool. Yeah, looking forward to the talks that follow, and it's good to see that there's still dot proofs around, and that it's and there's progress. Yeah. Are you still doing a lot with Coq?
I am doing a little bit, yeah. I'm doing some family polymorphism in Coq and things like that.
Okay.
We're trying to apply it to Coq, actually. So trying to do more modular proofs in Coq using family polymorphism.
How do you express family polymorphism in Coq?
Well, we're still working on this, but for now we're using the records and sort of encodings with like the functional encodings of objects and things like that. So
okay, yeah, I see. Yeah. Okay, cool. Yeah, we're preparing one submission for PLDI
nice.
about the match types, and that also was a recent effort with Coq to prove it in Coq.
Cool.
So that's
who led the effort?
Well, the hand proof was done by Olivier, and Jonathan did the Coq proof. So he learned the Coq thing.
Okay.
He was before he did everything in Idris, but for that one he switched, and that one it seems he said it was not very hard because it was very close to this Coq tutorial for Popple, which also was because essentially they're both based on FSUB. So
okay, yeah.
So that helps. Yeah.
By the way, I'm just wondering whether we need to track down more speakers because we have Nicola, and I'm not sure. I mean, I'm not sure who else we have from the list.
Did anybody drop out officially, or there just are no shows?
Unfortunately, not officially.
Okay.
There's only one person, Muhammad Reza Ashuri, who mentioned that he will be later here. But
I can ping Shaddai. I have this email.
I just pinged him very briefly.
Okay.
Okay, so I guess we'll see what happens.
Yeah. Okay. Good. Yeah. Okay.
And so Feng Yun has graduated, or he's graduating?
Yes, he gave a talk this morning, or last night. This morning it's crazy with this 12-hour rotating things that we always have two talks. Yeah. He is graduated. He's currently with the Scala Center.
Okay.
He's I think on the job market for next year, but for the moment they decided they wanted to stay in Lausanne.
Okay.
So he's got he's helping with the Scala 3 release, which is very very welcome. Yeah. Because as you can imagine, there's lots and lots of things and to be done. And,
yeah. I mean, I guess it's hard to anticipate everything as well, like that needs to be done,
yeah, we're sort of in the final countdown. Yeah, we still want to go into the first RC before Christmas, so we have another 4 weeks, 5 weeks, and then it's done. Modular bugs and stuff like that. Then, but hopefully, really early next year we're done with it. So that's the plan.
Exciting.
Yeah, it is. Yeah, yeah. But it's good. I mean, there are lots and lots of people involved now. I think if we have an all hands meeting, we're like 20 or something like that.
Oh wow! Okay.
Yeah. That's LAMP and Scala Center and Lightband a little bit, and Virtus Lab has now I think four people on the job or something like that. So they're investing a lot in it.
Okay.
And so they're doing so they do IDE and DocTool, and now they're starting to help with the compiler as well. So, and then Feng Yong. So basically, we have now LAMP. For the moment, we have 2 engineers, Feng Yong and Anatoly. And so it's a lot. And Daria is managing it all. So that's good. So. Because as you can imagine, it's a big management job to get everything lined up and make sure that nobody is blocked and all these things. Yeah. But I'm quite positive. I think we have it pretty much under control. So yeah, I spent most of August and September recording. I did all the MOOCs, redid all the MOOCs.
Oh, to use, is it, I mean, did you redo them for Scala 3, or did you redo them just because you wanted to improve?
No, for Scala 3, yeah. There's some new contents, but it's mostly the same. It's just that because the language is different, there's some difference in the way things are presented and the order, and there's some new topics. So extension methods and enums and opaque types, implicit function types. So so there are a few, and then of course since we now have indentation syntax. It meant that every slide had to be thrown out, and that means also every session had to be redone because you can't really essentially change the syntax.
Did you convert the slides automatically, or?
Yeah, mostly. Yeah, most of it by grateful. I didn't write a program. It was just search and replace and stuff like that.
Ah, okay.
Yeah. I mean, but no, then I had to go over it with a fine comb, of course.
Yeah.
What's the state of teaching?
So we taught it now for the second time at EPFL. The first time was last year, and and now it's basically when it's going to be released, then we're going to switch the Coursera MOOCs on for Scala 3. So yeah, that's a big effort. That's sort of the collateral damage of changing the syntax of a language. That you have to change everything. Otherwise, docs. There's lots of other doc efforts. This 47 Degrees and Virtus Lab and Lunatech. There are lots of companies now sort of jumping on it and trying to do docs for it and things like that. So yeah, I hope it will simplify teaching. I think some things were definitely net benefits, but not the ones I expected, interestingly. But that's maybe the way we teach the course. So I thought enums would be big, so to say, but then they turned out to be actually rather annoying because they give you this sort of second view on things. But I think that's because the course as it is, because it comes from structure and interpretation of computer programming, it's really very much this sort of closures are objects, objects are closures thing. And so it's very much to essentially lambda for everything. And then a pure data approach doesn't really work that well with that. So that's sort of. So then in the end, I thought first we tried to put them very early, and then now we essentially do sort of the normal approach to how we do data. And then at the end, we say, well, if you have lots of data, then this is actually a way to simplify it and make it more concise. But we didn't put it front and center in a sense. Because I tried, and Julian tried, and in the end, it was a mess. It was really so sort of you can do it this way or you can do it that way. And that's never good. Anyway.
Yeah.
Hey, great. I think Sade and Kushik have joined the Sumo.
Cool.
Maybe you can also quickly check out whether you can share your screen correctly. And yeah. Mm-hmm.
Are we starting now again?
Yeah, we should be starting. Maybe let's just check for. Hey.
Yeah. Hi. Just give me like 1 or 2 minutes. I'll set up my screen share.
Okay. Shall I?
Are we starting now? I thought it was 10. Or did things get shuffled around?
It's not your turn yet. We will first go with.
Oh, okay. Cool. I just. Okay. Never mind.
But you still may want to try if a screen sharing works or not. Do you want to test it, or should we go with the talk by Nicholas just?
I think it'll be okay. I was just screen sharing in another meeting earlier.
All right. So I guess, Guido, I pass on to you the session chair role.
Or David, would you like to go ahead? Is it okay?
Maybe. Okay, then welcome back to the second session of the Scala Symposium today. I'm pleased to announce that we will have this first talk of the second session out of order by Nicholas Stuckey about semantics preserving inlining for metaprogramming. Here's the stage.
So should I start or?
Yeah, please start.
Yep. Sharing. Okay, do you see my screen?
Yeah, I think it works. During the talk, the other persons can maybe also disable their video, and then after the talk, we can have a few questions from the audience. You can also try to write questions during the talk into the chat if you have any, and then we can check whether there are some. Okay, now you can start your talk.
Okay, so I'm going to present the semantics preserving inlining for metaprogramming. That was work that we did with Agelos Bigudi, Sebastian Duran, and Martin in the Lampa TPFL. I'm going to first quickly go to what I mean with semantic inlining. It's basically against what is syntactic inlining. Then we'll quickly see what is the relationship between inlining and metaprogramming in Scala or Scala 3. Then we'll see how we do the semantic preservation with inlining. Then we'll go into deeper into what are the interactions between inlining and object-oriented programming. And last but not least, we'll see an orthogonal feature which is called transparent inlining. So first, where macro started with syntactic inlining, and that means that basically this macro that is defined in C or C++ will just take the textual representation of whatever it has, inline it, and then it will try to type the program. This is extremely flexible, but it has a complexity for the user of the macro, because you can do whatever you want with that syntax, move it whatever you want, however you want, and you might then get an error from some code that you don't even see. On the other hand, semantic inlining is basically just a normal function call where we're going to first type check the body of the function itself to make sure. In this case, we know that A is an int, B is also an int, and we know that the whole definition of max type checks. And at the call side, we're also going to type check before we inline. In this system, inlining is basically beta reduction, a step of evaluation, but that it doesn't really happen at runtime, but instead happens at compile time. This can be done in two ways. Either we can guarantee that we inline, or we can do a best effort. So we chose guaranteed because we wanted to use it for metaprogramming, and we couldn't use the other one. And best effort is usually used for optimizations. For example, the JVM will try to inline whatever code it sees fit at runtime. So taking a step back into Scala 2, this is a Scala 2 macro, or the definition of the implementation has some shortened names for the types, but the main idea is there. So we basically have the macro itself, which is def power, and then we have this magic keyword macro imp that tells us that whenever we call this thing, we're actually going to evaluate the imp method at compile time, and this will return us some code that we'll use to replace this call. So there is a bit of magic here, and it's not clear what is the interaction between those two is. But in Scala 3, instead of doing it with, we do it with less magic. The first thing that we did was split the concept into two parts. One, which is inlining, we'll just inline some code. And then the other part, which is what really makes the metaprogramming part of this, is that this code that is inside of the splice will be inside of the splice that has a $sign, will be evaluated at compile time, and the code that will result from that evaluation will be inserted wherever we want. And here we also want to guarantee that whenever we inline it with the correct semantics. And then we do the macro can have its own special semantics, but it will do it following whatever the function call told it to do. So the first thing here is we need to make sure that we evaluate the definition correctly. So if you have this definition of max as before, and we call it with x and y, we're going to generate some vals to make sure that the parameters are evaluated in the correct order and that they are evaluated only once. Of course, this can be optimized away in some cases when we see that this x and y are pure and maybe only used once or used in the correct order, so we can just elide those values. But in general, we cannot elide them all the time because we might end up, if we inline x directly, we might evaluate this the ax twice because we refer to a twice. But Scala has other kind of parameters. So the first one is by name parameters, which, as their name indicates, they're going to be evaluated 0 or more times, and they will be evaluated each time we refer to it. So in this case, we are going to evaluate a twice if we go into the then part of the if, and we're going to evaluate b twice. And we also add another kind of parameter, which is the inline parameter, which basically has the same semantics as a by name parameter evaluation-wise, but code generation-wise is quite different. So the by name will generate a def instead of a val, and the inline will, as the names indicates, just be inlined. So the difference here is that with the normal by name, we're guaranteed that the compiler will do exactly the same as it usually does and will not start duplicating the code that is inside of the parameter. If we passed something, so a really long code instead of x, we would have to duplicate all that code. But instead, with inline, we'll just say, trust me, I know what I'm doing. I'm going to inline it, and maybe I'm going to use the knowledge of what b is and remove it completely from the code. Now, we also can support arbitrary recursion. In this case, we have a power function which calls itself in line 3. But for this to work, we need to make sure that this loop is not infinite, because this loop will actually unroll at compile time. So here there is an important thing, and it's that we added a new metaprogramming concept, which is the inline if. And what happens with this inline if is that if the condition partially evaluates to a constant, either true or false at compile time, then we're going to that code eliminate one of the branches, and we're only going to keep one of the branches, which will make us stop this loop. And in this case, we also have a third branch where if we don't have a constant for n, we're going to end up calling this error method, and this error method will just emit an error if it's in line somewhere, and not that eliminated by the ifs. And in this example, it will only happen if the n is unknown or it's a negative number. It's also it's important to keep the semantics clear for overloading. So whenever we call an inline definition, we choose the inline definition with the same rules as we would with normal definitions, because as far as we're concerned, it's just a normal function call. But when we inline this call, we need to be really careful, because here we see that we're inlining a call to log, but it's a call to log which is defined in line number 2. And because we don't know what the T is, we cannot call log in line number 1. But when we inline it, we need to still keep calling this version of log, because if not, we would be changing the semantics. In this case, we would just be printing something different. Even though we would have the temptation to say, oh, but we can actually call log. Once we inline, we know that it's an int, and we could potentially call the other log, but we shouldn't, because that would be a change in semantics. And in general, this initial elaboration that is done in the inline definition must be retained and not changed. And this also covers implicit resolution and implicit conversions that are done in typing of the body of the inline def. What we can do is perform devirtualization of calls to have to know more precisely which method we dispatch at runtime. If, for example, we're accessing some private field or package private or protected field in an inline, once we inline, we need to make sure that we can actually access this variable. For that, we generate accessors whenever the inline body of the function refers to something that is private. These kinds of bridges are usually quite small, and the JVM can optimize them away. Now into something that is a bit more tricky, which is what do we do with when we want to implement or override a method. So let's say we have this def max, which is in a trait, which is a normal method, and then we want to implement it with an inline, so that whenever we call nat.max, we want to inline the code, but then we also have it available if we call it on num. The tricky part here is that we can do it, but if we do that, we need to retain the body of the inline def. We cannot remove it from the bytecode. In contrast, if we didn't have to do this, we are ensured that every call to a method would be inline, and hence we don't actually need to remove it. We don't need to keep it in the bytecode. So in this case, we're going to actually keep whatever is in the right-hand side of the inline def and compile it as a normal method, and we're going to inline it whenever we actually know that we're calling directly nat.max. This works for implementing or overriding a method. There is another tricky thing, and it's if you're for this to work, or for the method to be retainable, we need to make sure that we can generate the body of that max function at compile time. For example, we could not have used the error method that I showed before, because that would produce an error whenever we try to compile this max. That also happens with if we use macros. If the macro cannot generate a generic version that can be placed in there, then we cannot use it. Now, a quite similar situation is if we have an inline def, and then we want to override it with a normal definition or with an inline definition. So here the problem is that we won't be able to do it. And the issue is that if we call num.max directly, then we're going to inline the code of null.max directly. But if at runtime the value that we actually passed to it was a nat, then we should actually be calling nat.max, which we will never do, because we remove the overload resolution at runtime, and yeah, we end up in a situation where we always call the num.max, and for that reason, all inline definitions must be final. We don't need to write final. We just assume that they're all final in the code. So in general, there are other concerns, like what can we have abstract inline definitions and what to do with inline parameters. I won't go into details on all those things, but there are a few short rules that cover all the cases. So inline methods must be final. If a method implements or overrides, if an inline method implements or overrides a normal method, then it must be retained. Retained methods cannot contain inline parameters, and an abstract inline method can only be implemented by an inline method. That has its uses. It's a bit weird, but if you want to know about it, just check the examples in the paper. And last but not least, we have this transparent inline, which does something slightly different. So here, what we want is to say that we have this set_for function that takes some type parameter, and we want to create a set for it. But we want this set_for function to return us a tree set if we know that there is an order for that type, or a hash set if we don't have an order. So if we look at the signature, we can see that it returns a set. So this wouldn't work. But whenever with a normal inline definition or with a normal def. But by adding the transparent inline, whenever we inline this definition, we're going to refine the type of this call and take the more precise type of whatever was inlined. This gives us something more powerful than what we had, but it's still not this syntactic inlining power that other metaprogramming have. So it's a more controlled way to do to influence the typing at call site. And in this case, we implemented this using this summon from method, or actually metaprogramming feature, which will just look for an implicit ordering of t. But instead of doing it before we inline, it will do it after we inline. This means that to call this set_for, we actually don't need the ordering. So we can optionally find it or not, and then do something different in both cases. That's all. Any questions?
Thanks for your talk. Good to know about inline methods in Scala. I would start with the first question. Namely, I think there's a proposal for inline classes also for the Java programming language, which is another name for value classes, which should be related to case classes in Scala.
Yes.
Is there something you can say about that relation?
Well, it's not that directly related, but yeah, the other one is more about a runtime representation of those things. So it's
oh, right. I just remember in your talk you explicitly mentioned that inline is mostly for def bindings for methods, whereas
yes.
in the other case it's for classes, right? Do you think?
Yes,
do you think inline would also make sense for classes in Scala, or for other bindings except defs?
Well, the concept that would match that would be more value classes directly. So we already have value classes or opaque types to cover some of those cases, but it's not exactly the same use case as here. It's some other kind of inlining.
Okay. If anyone else has a question, you can also unmute himself and ask it directly.
Yeah, I have a question. So, what are some interesting use cases of this? Like, I mean, I guess you've explored some applications, and I'm curious what came out as something surprising or interesting.
Surprising? Well, the use cases are mostly macros. And maybe surprising, we could do some amount of specialization of primitive types out of the box with this. We are missing some things in boundaries where we cannot specialize. One example is exactly for classes, which actually might be fixed if we have the combination of value classes on the JVM and this. Or maybe we don't even need, the value classes would cover everything, depending on how they materialize exactly.
Cool, thanks.
Okay, I guess that was a great talk, and we can move on to the next. I think now actually we have the case that we have two speakers finally there that could theoretically give their talk. Now in the actual timeline, Shadai would be next. Muhammad, would it also be okay if you take the slot after this, and then your talk would be in 20 minutes, and then you have two talks one after another? Would that be okay, Muhammad? Reza? You have to unmute yourself.
Yeah, hello. Yeah, I'm flexible about that. So if there is someone else who wants to take the next talk, I'm okay with that. But if there is nobody, then I can take it.
Okay, then I think we can have at least one talk that's actually in schedule and go to Shadai right now. Okay, then it's my pleasure to announce the talk ScalaPy, Seamless Python Interoperability for Cross-Platform Scala Programs by Shadai Ladat, who will tell us how to integrate Python and Scala.
Cool. Yeah, let me share my screen. All right. Can everyone see this?
Yeah, I can see it.
Okay, awesome, cool. Hi, everyone. I'm Shadaj. I'm a third-year undergraduate student at UC Berkeley. I'm studying electrical engineering and computer science. This is joint work with my advisor, Professor Kaushik Sen. So this talk is about ScalaPy, a seamless Python interoperability layer for cross-platform Python programs. So before we kind of jump into the details, let's talk about why ScalaPy matters. Today, data science has a bit of a split ecosystem. We have a lot of powerful tools available in Scala for dealing with large data sets, and we see Scala being used in a lot of production environments. But on the other hand, Python is proving to be very useful for data scientists who are exploring data and trying to do some initial exploration with different types of machine learning models and statistical analyses. And so there's kind of a split where you have these libraries focused on experimentation in Python versus libraries focused on production in Scala. And we kind of see this in the type of specific libraries that are available, right? Scala has things like Spark, which is really geared towards these large-scale production uses, whereas you have things like NumPy, which are just focused on giving you a really rich API for linear algebra. And so the goal of ScalaPy is to bring these two languages together so that we can get the best of both worlds and use a single language, Scala, so that we don't have to context switch between these two languages all the time when working on data science. And so that was the goal. How can we bring Python and Scala together? And ScalaPy makes that possible. So there are 4 core things that ScalaPy lets you do. It lets you use Python libraries from Scala code. It lets you do that in both JVM and native code. So we support Scala native for a much faster interop layer. You get a seamless interoperability layer. So you can take code that you see in Python examples and port them to Scala super easily. And you can mix and match Python and Scala values around in your code. And you can have a fully type-safe interface. So like existing interop layers and kind of language integrations for Scala, like Scala.js, ScalaPy also gives you the support for defining custom type facades that let you wrap over Python values to interact with them in a type-safe manner. So I'm going to do a really quick live demo just so that y'all get a feel for the type of APIs that you get in ScalaPy. So ScalaPy supports Jupyter notebooks out of the box. That's one of the core features, is to support types of development workflows that are expected for Python developers. So I'm going to start by importing ScalaPy. This is going to pull down a bunch of stuff from Maven Central, and we have it imported. In this example, we're going to do a very simple linear regression, but we're going to use TensorFlow to do that. So I'm going to start by importing two modules. So here we have a special API, py.module, for importing a Python module. You'll notice here that we're using TensorFlow, which normally won't necessarily work with all types of interop layers because it depends on native bindings. ScalaPy works with any Python library, regardless of what native dependencies it has. We also support things like operator overloading. So here we have xdata, which is a reference to a NumPy array, but we're able to use the times operator, and that's passed through into the original Python operator implementation. Next, I'm going to initialize some TensorFlow variables, which are going to represent our slope and y-intercept. You'll notice here that I'm taking a Scala sequence and converting it into a Python list. This is one of the interesting seamless kind of components of ScalaPy, of converting between Scala and Python collections. And you'll see what this toPython proxy thing does later in the talk. Next, we're going to set up our optimizer to reduce the mean squared loss. And so we have that set up. And lastly, we'll run a 200 iterations of training. And every 20 steps will print out what we've predicted. And we're able to see that we're able to predict correctly the slope and y-intercept. And so here we're able to use TensorFlow, which has these really nice high-level APIs from Scala without any issues, and we're able to mix them really seamlessly. So that's the power of ScalaPy. And so with that, let's jump into how it works. So first, let's talk about how ScalaPy talks to Python. So ScalaPy works by embedding Python. This is a bit different than kind of, I guess, existing approaches for language interop in Scala, where Scala usually compiles to the language. Instead, for ScalaPy, since we know that there are existing production environments on the JVM and hopefully soon in Scala native, we want to support ScalaPy as a library layer. So ScalaPy sits as a library inside both of these environments and instantiates an instance of the CPython interpreter. This is a standard interpreter, and that's what lets us use libraries like TensorFlow, which have native bindings. The only difference between these two platforms is how we bind to the interpreter. On the JVM, we use JNA, and in Scala native, we use the native APIs for foreign function interface to C. And then all of the logic for actually communicating between ScalaPy and the CPython interpreter is actually shared across both of these platforms. So on the CPython interpreter, we might have some values, and these are in the Python heap. So you might have an array or a reference to a module. There are two levels in ScalaPy for referencing these. At the first level, we have PyValue. So PyValues are these opaque, untyped references to CPython values. They handle things like garbage collection and heap synchronization between Scala and Python, but they don't actually give you any nice high-level APIs. They're just kind of references to Python. But what we do is we add an additional layer on top of these, which is typed, and that is what you actually interact with at the high level when you're a user kind of manipulating Python objects. So you never actually see these PyValues, but the PyValues are what does the work underneath of making sure that references from Scala to Python are maintained properly. Now, one of the really interesting things that ScalaPy offers is this cross-platform binding. So ScalaPy supports both the JVM and Scala native. On the JVM, performance isn't as great because you have this additional cost of JNI and JNA going across this boundary. But in Scala native, you get really fast interop because it's as if it's just another function call. What we're able to do is, because JNA has a similar model to Scala native in terms of you're able to reference things like pointers as just objects, we're able to have a very thin kind of cross-platform layer where we create type aliases which correspond to the equivalent type on JNA or Scala native. So in Scala native, a pointer is a pointer of bytes. On JNA, it's a pointer. We also have things like an abstraction around zone allocation, which is required in Scala native, but not in JNA. And so by just having these kind of core abstractions, we're able to write a bunch of cross-platform code that actually deals with the Python APIs instead of having to rewrite the logic and risk having different runtime semantics. Also, we have to handle the fact that Python executes in a single thread, whereas Scala is fundamentally a multi-threaded concurrent language. So one thing that we do is make sure that even if you're accessing Python values from multiple threads in Scala, all your references will be safe. And so we do this by acquiring the global interpreter lock in Python. But what we've noticed is even though this lock is blocking kind of individual calls into Python, this actually doesn't impact performance as much because most of the time you're using some library like TensorFlow or NumPy, which go into native code. And that native code actually releases the lock while it's sitting there. So you're only holding this lock for a small portion while you're jumping between the two worlds. Next, let's talk about how we mix these two languages seamlessly. So at the top level, you start with dynamically typed APIs. So just like Scala.js has js.dynamic, we have py.dynamic. The reason we offer this dynamically typed API is it makes it really easy to get up and running with your favorite Python libraries. You don't have to go through all the effort of defining static types. You can just get started right away. So we can create things like a list, and we use the regular Scala.dynamic to handle calls out to Python. So in some situations, you might also have some custom Python snippets. Maybe you found some quick solution on Stack Overflow, and you're too lazy to convert it over into Scala. So something you can do is use this Python interpolator, which lets you write snippets of Python code, but also use interpolation to kind of embed bits of references to Scala or kind of Python Scala Py values. And so what this will end up doing is creating a temporary local scope inside the Python interpreter, load these variables into that environment, and then just execute the Python string directly there. And so this makes it also even easier if you have some existing Python code that you want to port over to Scala Py. And lastly, the kind of other kind of aspect of Python that we have to bring over into Scala is custom syntax elements. So Python has some keywords like with, and we also have things like using square brackets to access arrays, which is not a thing in Scala. And so Scala Py offers equivalents for these through APIs. So for square brackets, we have dot bracket access, which we saw kind of in the Jupyter notebook. For with, which lets you kind of temporarily use a value and free it afterwards, we have this py.with, where you pass in first the parameter, the value that you want to temporarily use, and then a function of what to do with that value once you have it loaded. So here we can use it to load a file, for example. Next, we have kind of more complex situations, and Scala Py's goal is to make sure that all types of Scala values can be brought over into Python and vice versa. So one of the components of supporting that is supporting the conversion of Scala functions into Python lambdas. So for example, in this situation, we can call the Python map function, but pass in a Scala function and get the correct results. So how does this work under the hood? So we have, again, Scala Py and the CPython interpreter, our picture from earlier. We have a Scala function that we want to send over into Python. Now, what we do is we start by making sure that Python can reference that Scala value safely. We do this by creating this kind of reverse reference manager, which will keep that Scala value alive as long as this tracker, which kind of mirrors this Scala value, is alive in the CPython interpreter. And so you have this binding between the tracker and this reverse reference manager. Then we create a general handler. So when you're creating a lambda in Python, you have to create it using just a regular C function pointer, which means that we need a static function. We can't have anything that's dealing with closures to pass in as that C function pointer. So we create this general handler for all converted lambdas. And this general handler will try to look up what its own tracker is, pull that from the reverse reference manager, and call the associated Scala function. And so when we create our final lambda, which is the result of this conversion, the lambda will be implemented by the general handler, but it will also store the tracker under the hood so that when the lambda is called, this tracker can be looked up and then the original Scala function can be looked up. So a bit of how this kind of works under the hood is we have this lambda handler, which is that general handler. All it really does is unwrap the tracker object, which is stored inside of the lambda, grab that value, cast it into a regular Scala function and call it. And then on the other hand, when you're converting a function into a Python lambda, we do a little bit of rewiring since Python presents multiple arguments as just a tuple. And so we unwrap those. And then on both ends, since our function might be using Scala types, but we want to send this into Python, and Python will be calling it with Python types, we perform automatic conversions between the input Python values to the input Scala values and the output Scala value to the output Python values. So we perform conversions on both ends so that both sides can deal with values the way they'd like to. Next, we also support sequences. So ScalaPy supports the automatic conversions of Scala sequences into Python values. We have two different APIs for these to support kind of two different types of semantics. So first, we have toPython proxy, which creates a very thin layer and results in semantics that when Python requests an element, that value will be grabbed from the sequence on demand. So you can see here, if we have a side effecting apply, that means that as the Python proxy is being loaded, we'll be requesting those indexes from the original Scala sequence. So this is really nice for low memory utilization and kind of being lazy with the conversion of values. But in some situations, if you have a large data set that you know Python will be accessing very frequently, you want to instead copy the data over into the Python interpreter. And so we offer an API for that as well, which just copies the data instead. The proxy collections are a bit interesting because that requires Python to talk back to Scala. But one of the nice things is because we already have the support for converting Scala functions into lambdas, we can just use this for proxies. So what we do is if we have a Scala collection with an apply, we'll create a Scala function, which references that apply method, convert that into a Python lambda, which is an equivalent for that apply method. And then lastly, just wire the Python sequences get item to that lambda. And so now we have a Python sequence, and whenever you try to access an element, it'll go to Scala and grab that element for you. And the automatic type conversions that I discussed earlier between kind of Python values and Scala values when you're calling this function will be invoked here as well. So you'll get, if you have a Scala collection of ints, you'll get a Python sequence of Python ints on the other end. So a bit of how this works under the hood, we just actually set up a simple class which says what are the functions to use for getting an item and getting the length. And we just proxy out to those. But these functions will actually be backed by Scala functions. And lastly, let's talk about maintaining type safety, which is something that's super important, especially for us as Scala developers. Type safety is really important since it allows us to program with a lot more confidence. So first of all, ScalaPy comes with some built-in type mappings between Scala primitives and Python primitives. So these are between kind of the core built-in types of Python. But beyond this, ScalaPy also comes with a complete type hierarchy of all the different types of values you'll get in the Python standard library and ecosystem in general. And so these are the types of values that you get when you're loading a module or kind of calling Python APIs, you'll get back these values. And so we have this mirror of the actual Python type hierarchy that sits in Python, and we mirror that into Scala. And so this makes it easy to kind of deal with individual modules from the standard library without sacrificing type safety. But if you're dealing with modules outside the standard library, you'll want to define type facades yourself. So for example, in this case, if you want to define a facade for the random module, we can do that using a syntax that's very reminiscent of Scala.js and Scala native. You just do @py.native, just like js.native. You define a trait. You can extend other Python values to kind of create that hierarchy of types. And then you just declare that I have random exposes a uniform method that takes 2 doubles and returns a double. And so now you can cast a Python value into that facade using .as, and now all of your uses of that value will be type checked against this random trait. What this works under the hood is we actually just synthesize a instance of the reader type class, which constructs an instance of random with the underlying value set to the original underlying value of this module. So we kind of rewire the same pi value to be under the hood of this new type facade. And this makes it easy to do safe data science. So if you're using something like NumPy, you can now write a lot of code with confidence that you won't get halfway through your training and then your program will crash, which is never a fun experience. So you can do data science with a lot more confidence. And a really cool thing is that members of the ScalaPy community have kind of extended this to add even more advanced features. So for example, Maxime Kajer, who's a master's student at EPFL, developed this library called TensorFlow Dotty, which uses some of the advanced type features of Dotty along with ScalaPy to give you shape-safe computations with TensorFlow. So for example, it can make sure that when you're reshaping, the product of the dimensions match. If you're reducing by the mean on a single dimension, you are kind of using the right dimensions depending on your output type. So this makes it even easier to do type-safe data science. So in conclusion, Scala pilots use Python libraries from Scala code. You can do this in both JVM and native code. You get a seamless interoperability layer and a fully type-safe interface. So you can get started today. ScalaPy is open source on GitHub. And now I'd like to answer any questions.
Hey, great talk. Seamless interoperability for Scala and Python. Sounds like a lot of effort. And the talk was also great. You actually answered some of the questions that I had during the talk in the order that I came up with the questions. If someone from the audience has a question, just unmute yourself and make yourself available. Otherwise, I would start with a question.
I have a question.
Okay.
So these facades for external Python modules, do you always have to write these yourself, or do you have a library of them? Or because I don't want to write a facade for every Python module that I import.
Yeah. Okay. So this is actually a slide I dropped from the talk for today because I wasn't sure if I should focus on just what's in the paper, but something that's coming soon that's kind of in the pipeline is auto-generating type facades for libraries. So Python now has optional type hints. So for quite a few of the mainstream libraries, these are actually enough to generate full Scala static type facades. For now, you do have to write your facades by hand for kind of each module. There are a couple kind of built in. So there are already some facades available for NumPy and TensorFlow, but soon you'll be able to get facades for basically any mainstream library you want by auto-generating them.
All right, that's cool. Yeah, I think it's a smart idea to reuse the Python type hints for that. Thanks.
I have a question. If you do, with the Python interop, you have a Python heap and a Scala heap. So how do you synchronize the two?
Yeah, so that's kind of where the PyValue comes in. So PyValue on the JVM uses finalizers to determine when you can clean out a reference to the underlying Python value, and we update the reference counts for that Python value appropriately. On Scala Native, we don't have finalizers, so we instead have this py.local construct, which acts as a zone. So any Python values allocated within that zone or any references that are created in that zone will be freed at the end of that. And then in the reverse direction, because Python can reference Scala values, we have this reverse reference manager. So we use finalizers on the Python end as well. So once we know that we don't have that reference anymore, we can drop the reference on the Scala end.
Okay, thank you.
Okay, I would have a question, namely, I assume Python to Python and Scala to Scala calls are probably much faster than Python to Scala and Scala to Python calls, right? And furthermore, I think many Python libs are actually C libs, wrappers around C libs. So you would additionally have the overhead of from Scala to Python to C and back. Is there something you can say about that? Does it occur in practice?
Yeah. So unfortunately, there's not too much we can do, unfortunately. I guess a lot of the Python ecosystem has ended up in this situation where, yeah, most of these libraries are wrappers around C libraries, but you end up having quite a bit of logic in Python itself. Like that's one of the issues with TensorFlow is TensorFlow actually has quite a bit of high-level logic in the Python code. So we have to kind of go directly to Python instead of directly to C. One of the nice things though, and kind of this is the thesis of ScalaPy and why we chose like JNI, which is not as fast as JNI, but gives us kind of an easier interop layer, is that when you're dealing with data science, most of your time is being spent in that native code. And so you're kind of this portion of Scala going into C is kind of negligible to the amount of time you're going to spend on a GPU processing some gradients and things like that. And so in most situations, it won't really be that noticeable.
Okay, great. Do we have more questions? Okay, it doesn't seem to be the case. Someone asked about generating types. Would that also involve types like from MyPy or generating type facades? In Python, there's also this typing annotations that are new, which can be checked via the MyPy tool. Is that about that? Or,
yeah. So we're actually using MyPy under the hood for extracting those type annotations, getting them into a nice parsed format so that we don't have to parse them ourselves. And then we kind of navigate that graph of types to generate the Scala facades.
Okay, great. If there are no more questions, then I would go to the next one. Thanks today. Now it's Mohammad Riza's turn, right?
Okay. Hello.
Okay, then
So I'm going to share my screen. Can you hear me?
Yes, we can hear you.
Okay, great. So,
but we can't see your screen yet. Can you? Oh, okay. There. Okay. Okay. Then it's my pleasure to announce the second to last talk for the Scala Symposium. It's about Kaizen, a scalable Concolic fuzzing tool for Scala, and you can start now.
okay, yeah. Hello, everyone. My name is Mohammad Reza Ashuri, and I'm from University of Potsdam. In this presentation, I'm going to introduce Kaizen as a scalable Concolic fuzzing tool for Scala. So Scala is as you know, Scala is a general purpose compiler that supports functional programming language and has a powerful static type system. The main compilers run on the Java Virtual Machine or JVM. In addition to JVM, it's possible to write Scala programs for web browsers using a specific compiler called Scala.js. Also, Scala Native is another compiler that targets the LLVM infrastructure. In this work, we focus only on Scala C, specifically 2.x. Although Scala and Java are both JVM-based languages, Scala is more extensive than Java. In other words, Scala includes both object-oriented and functional programming into one compiler. Scala has all the advantages of Java platform, and it works with nearly all Java libraries, except it doesn't maintain backward compatibilities. Furthermore, Scala has more type safety features than Java. For instance, Scala contains static types that help to reduce tricky errors during execution time. And it uses actor model for setting functional concurrency, whereas Java uses traditional thread-based model for concurrency. And finally, Scala core frameworks are play, lift, echo, while Java core functions are Spring, struts, Hibernate, and so on. So now we talk a little bit, we are going to talk a little bit about vulnerabilities and security in this ecosystem. So despite the safety capabilities of Java, software development is still a human initiated and error-prone task. So developing super safe programs requires in-depth knowledge and experience in terms of security analysis in target ecosystem. For instance, if programmers forget to check untrusted input coming from external environments, such as network, web form file system, other processes, etc., we might have some vulnerabilities in the code. Therefore, it's suggested to fix sanitization errors and the other type of errors while our code is still under the development phase. However, due to the cost of code review and tight deadlines, programmers often do not perform in-depth security analysis. Hence, using effective automatic mechanism for identifying security vulnerabilities, especially on the binary level, can be an advantage to improve the overall security of any programming ecosystem, such as Scala. So mainly there are two options to perform security analysis on a program level, namely static analysis and dynamic analysis. Static analysis is mostly used when we have the source code, often during the development phase. And in a nutshell, in this approach, we scan the source code without actually executing that. However, due to the lack of access to actual runtime information, the generated results are often imprecise with lots of false positives. The other downside of static analysis is requiring the source code requirement, which is usually unavailable for real-world commercial software. There are a few static analysis tools ported from Java to Scala that often produce substantial false positive results and do not support many internal components of Scala frameworks. On the other hand, we have dynamic analysis. In this technique, we don't need to have the source code and we have access to runtime data. However, it's not as sound as static analysis, but the results are mostly more accurate. Accordingly, in this work, I introduced Kaizen as the first Scala-specific security analysis tool that works based on Concolic fuzzing for evaluating real-world Scala applications and binary files. As you can see, Kaizen works based on three main stages, namely graph analysis, Concolic testing, and dynamic execution. In Kaizen, we consider an executable path exploitable when it has at least one sync method. So what is a sync method? It's any method, any programming method that deals with sensitive data or operations, such as databases, such as process management, file system, external devices, etc. For finding these paths, we first generate the call graph of input application in order to find data dependencies between the variables. In this step, actually we aim to find potential exploitable paths in the target Scala application. After the call graph generation, Kaizen performs a backward slicing function that allows us to distinguish potential exploitable path from neutral or safe paths in the code. Afterwards, we perform, basically prune non-exploitable paths in order to increase the results accuracy and reduce potential false positives. So how we classify non-exploitable path? So say any exploitable, executable path that doesn't include sensitive sync methods is non-exploitable path, and it must be removed from further analysis in Kaizen. So here you can see some of the sync methods in a Scala ecosystem that actually we define for Kaizen. In the next step, Kaizen performs Concolic testing. So for those of you who are not familiar with Concolic testing, in a nutshell, it's a combination of concrete and symbolic testing. It's a powerful program verification technique that performs symbolic execution, and its main focus is on discovering bugs in real-world software. So in Kaizen, after receiving an exploitable path, we commence the Concolic testing module in order to check for the sanitization vulnerabilities of that given path by generating concrete values containing malicious comment to trigger the sync function in the code. So in this stage, we basically model the path as a logical formula. So the final formula is like f path union f source union f sync. So then we send this formula to the Z3 SMT solver to execute the selected path symbolically and collect a set of path constraints. The outcome of this operation is a set of concrete inputs that trigger certain exploitable paths based on satisfying values in the code. We designed a parallel Concolic testing engine in order to improve the overall performance. After generating concrete inputs for a target application, in the last step, Kaizen instruments the exploitable path. Then it executes the instrumented program along with the generated input. If the generated input can reach out the target sync without being sanitized at its argument, Kaizen confirms the lack of proper sanitization in that particular exploitable path. So note that for the bytecode instrumentation, we use JVM agent and shadow variable technique. Kaizen instrument the application on the fly. So in this part, I will show you the evaluation results. So to provide a real-world evaluation, we collected a benchmark suite, including 1,000 open source Scala projects available on GitHub. So our benchmark suite includes popular Scala projects such as Play Framework, Eka, Finch, and Slick. So we restricted our analysis time to only 10 minutes per each benchmark. So here you can see the summary of the identified vulnerabilities in the basically popular Scala projects. So how we consider them popular based on their stars and contribution size on GitHub. Here you can see the list of most frequently exploited sync methods in our benchmark suite during our experiment. So in our evaluation, we also measured Kaizen's runtime performance. To do this, we selected the Scala benchmark suite, which is a popular benchmark, a Scala benchmark that contains multiple microprograms for various domains. So here you can see the result of performance analysis. Kaizen basically only imposed 49% overhead. Regarding related works, because Kaizen is the first Scala-specific vulnerability analysis, it was very difficult to perform a sound comparison here because there was no actually any other available tool. However, we compared Kaizen with famous previous study for the JVM ecosystem. And we selected popular tools such as TaintDroid, FlowDroid, Scala Style, and Scapegoat. Here in this table, you can see the differences and advantages of Kaizen in comparison with previous study for the JVM ecosystem. So in conclusion, in this presentation, introduced Kaizen as an effective fuzzing tool for the Scala ecosystem. This tool takes the complexities of real-world Scala project into consideration. The main technique here is detecting and analyzing exploitable path, but by performing backward slicing and the call graph of given program, we used Z3 SMT solver in our Concolic engine in order to gain the maximum code coverage. And to demonstrate the usefulness of our approach, we collected 1,000 real-world Scala projects and performed our evaluation. And we finally could find 101 security issues. Thank you for your attention. Is there any question?
Okay, great talk. Again, if anyone has a question, he can just unmute himself and ask it directly. Otherwise, I have a first question. Concolic testing, you said you've used it to find exploits. Wouldn't you need to run unit tests or some form of tests to actually find something? Maybe you can explain a bit what kind of exploits you're finding or what you are testing?
Yes, it's a good question. Yeah, as I said, actually, first we basically, when we introduced a binary application to Kaizen, we first perform we try to extract the call graph. By doing that, we can actually find all the potential executable paths, right? And then we look for sensitive things. So we know, for example, that for SQL injection, for code execution, we are looking for particular things, particular Scala functions, as I actually showed you in the presentation, that they are dealing with that. For example, they are dealing with process management. They are dealing with file system, right? So by finding them, we specify them, and the next level, we perform backward slice. We try to find, okay, where is the source where actually we get the arbitrary any data from, for example, users or any untrusted source environment, right? For example, user input, web forms, network, whatsoever. And then we go and instrument that particular executable path. So by doing that, then we have basically this path. And the Concolic engine is responsible for generating satisfying values that trigger those paths and somehow reach out the sync methods, right? And by doing that, so we know that, for example, we define that, for example, for sync method that they are associated with SQL database, we can actually, we add some neutral exploits in our concrete value. And then we instrument application by executing that and monitoring that by the shadow variable technique. We can actually understand, is there any proper sanitization in this path or not in real world in the runtime? And if there is no, then we actually confirm, okay, we have SQL injection. So as you see, we found actually multiple vulnerabilities such as norm injection, stick injection, remote code execution, and so on in actually many popular frameworks in Scala. So that was my answer. If you need, I can actually give more details.
Okay, great. I think we have a question in the chat, which is by Guido. Maybe you want to ask it.
Oh, yeah, I can ask it myself. So I was wondering what in your work was more challenging about Scala compared to simpler languages, so to say.
It's a very good question. Actually, in comparison with like low levels of system programming languages, using Scala was an advantage because here actually we deal with the JVM structure and JVM bytecode level. So we actually are not worried about the different instructions in different architectures, right? So that was one of the actually main advantage of designing this system for Scala. And the other one was basically instrumentation. Instrumentation here, because I chose actually Scala C, was by, I performed that actually on the fly. So we didn't manipulate something on the disk. That was the second, I think, advantage. And the third one was the capability of JVM agents, because via agents, actually, we can manipulate the bytecode and perform shadow variable. And to be honest, yeah, I mean, it was a lot of advantage in comparison with low level like C and other programming languages. And I would say there wasn't a big challenge here.
Thank
you.
Okay, great. I guess we could move on to the next talk, but I heard that maybe we won't have a last talk. Is that the case?
Yes.
Okay. Then that was the last talk, and we're coming to an end for the Scala Symposium this year, and I will let Guido and Nada say something.
Yeah, I mean, not much to add from my side. So thanks everybody for being here. I really hope that we can meet in person soon, possibly at Scala Symposium 2021. And Nada?
Yeah, so I just had a few numbers from the program committee. So there was 5 full papers submitted, and we accepted only 3. And otherwise, there was the open source talk and 2 student talks, and these were accepted. And each submission was reviewed by 3 members of the program committee. And so, yeah, I just want to thank the program committee as well for all their work. And yeah, so that's it on the statistics side for the workshop.
All right, then thanks everybody, and see you next year at the Scala Symposium 2021.
Thank you.
Thanks.
Bye-bye.
Bye.
Bye.